Is there really anything in the universe? Our universe is a huge wonder, but sometimes we forget how empty it really is, and why exactly it's called space. As we get into the details of the universe, let's begin with something that is quite within our reach. Our solar system. Our solar system is a massive, interconnected system of celestial bodies bound together by gravity. Gravity is much more than what makes everything that goes up come down. It's an attractive force which makes everything in our solar system centered around one star, the Sun. Think of it as the gravitational powerhouse that keeps everything in check. In fact, many like to call the Sun the heart of the solar system. This glowing sphere is a G-type main sequence star, which is often called a yellow dwarf. It makes up about 99.86% of the solar system's total mass. It is equivalent to 1,000 Earths long and could fit all the 8 planets 600 times over. At its core, the Sun generates energy through nuclear fusion, transforms hydrogen into helium, and releases light and heat, the very things that make life on Earth possible. Earth is where all life begins and ends. Scientists believe it is because we're located in the habitable zone of the solar system, where all the conditions are perfect for life and growth. And unlike other planets in the system, Earth has complex systems that help run the planet and support all the forms of life found in it. The first is the atmosphere. It protects us from harmful solar radiation and helps all living things regulate temperature. The hydrosphere comprises all bodies of water, whether big or small. In this case, oceans cover about 71% of the Earth's surface. Perhaps the reason it exists so abundantly is because the hundreds of billions of living creatures on the planet require water for their survival. The geosphere is Earth's layered structure that drives plate tectonics and shapes mountains and continents. Then, the biosphere is home to all living organisms. This is primarily where they exist and biologically multiply to expand the circle of life. Big as it is, Earth is just one of the 8 major planets in our entire solar system, and these planets are divided into 2 categories based on their makeup. The rocky ones that are closer to the Sun and have solid surfaces are called rocky planets or terrestrial planets. In this category, there is Mercury, which is the smallest and closest planet to the Sun. Venus, Earth's twin in size, but with a thick, toxic atmosphere and intense heat. Earth, our home, and the only planet we know that supports life. And Mars, the red planet, which is known for volcanoes and deep canyons. The gaseous planets, on the other hand, also called the Jovian planets, are mostly made of gas or ice and have no solid surface. Here, there is Jupiter, the largest planet, with a storm called the Great Red Spot that's been raging for centuries. Saturn has a beautiful ring system made of ice and rock. Uranus is an ice giant spinning on its side, probably due to a collision that happened centuries ago. Neptune is also another ice giant with extremely powerful winds and dark storm systems. These planets, along with their moons and occasional ring systems, all orbit the Sun in elliptical paths in what scientists like to call a cosmic dance. Now, besides the major planets, there exist other lesser-known and smaller worlds that don't seem to dominate their orbits. These ones are called dwarf planets. The first of them all is Pluto, which was once a planet but is now in the Kuiper Belt. Ceres remains the only dwarf planet in the asteroid belt, between Mars and Jupiter. Haumea is a little stunner known for its odd elongated shape and fast spin. Makemake is more or less just a bright object in the Kuiper Belt. And the dwarf planet Eris was the big break that redefined Pluto's status. But how did this all come to be in the first place? About 4.6 billion years ago, a giant cloud of gas and dust collapsed under its own gravity to form a spinning disk. The Sun emerged at the center, and over time, particles in the disk clumped together to create planetesimals, which eventually became the planets, moons, and the smaller bodies we see today. There are solar systems beyond ours. Alpha Centauri is the closest star system to our own, and possibly our only gateway to understanding life beyond Earth. Although it is about 4 light-years away, it hasn't stopped scientists from making new discoveries from time to time. But the thing about Alpha Centauri is that it isn't one single star. It's a trio of unique stars. The first is Alpha Centauri A, also called Rigel Kentaurus. Centaurus is a yellowish star that's a little larger and brighter than our Sun. Think of it as the Sun's bigger, shinier sibling. The second is Alpha Centauri b, or Ptolemon. This one is a bit smaller and cooler than the Sun, and it glows with a beautiful orange hue. The third would be Proxima Centauri. This guy seems to be the odd one out. It's a faint red dwarf that holds the title of the closest star to Earth. But despite these distinct features, one would think that these stars interact similarly to how actual planets do. Well, it's quite different. Very interesting, if you ask. Alpha Centauri A and B are in a slow cosmic dance and will forever orbit each other every 8 years. However, the distance between them fluctuates and would usually range from about 11 to 36 times the distance between Earth and the Sun. Proxima Centauri, on the other hand, is the distant cousin. It orbits the pair from much farther out and takes about 550,000 years to complete one loop. Now, what about the actual planets? For years, astronomers have been hunting for planets in this system, and this is what they found so far. In 2016, scientists discovered an Earth-sized planet orbiting Proxima Centauri in its habitable zone and named it Proxima Centauri b. Then, back in 2012, a possible planet orbiting Alpha Centauri b was announced. They named this planet Alpha Centauri bb. However, follow-up research has questioned the entire existence of this planet. You see, studying solar systems besides our own helps us answer some of humanity's biggest questions. Because Alpha Centauri A and B being so similar to our Sun, we get to understand how stars like ours evolve and behave. Its proximity also makes it a prime candidate for searching for alien worlds, especially those that might actually support life. And if humanity ever ventures outside our solar system, Alpha Centauri will likely be the first stop. In fact, in 2016, Project Breakthrough Starshot was launched as an attempt to develop super-fast, light-driven spacecraft, known as nanocrafts, to explore Alpha Centauri. The primary goal of Breakthrough Starshot is to prove that it is possible to send these nanocrafts to Alpha Centauri at speeds reaching up to 20% of the speed of light. At such velocities, a journey that would normally take thousands of years could be completed in just over 20 years. However, these further explorations are not as easy as they sound. One particular reason being that Alpha Centauri A and B are so bright that their glare often overshadows any planets nearby. Besides, we're only just beginning to develop the tools sensitive enough to spot small Earth-like planets in systems like this. But despite the challenges, the future does look bright. Advancements in technology get us closer each day to cracking the codes of this neighboring system. Missions like the James Webb Space Telescope could help us spot planets or even study their atmospheres. Direct imaging techniques could also one day let us take actual pictures of planets around Alpha Centauri stars and help us assess their potential for life. But how could we talk about the world of solar systems and leave out the discussions of galaxies? They are like cosmic neighborhoods made of stars, planets, gas, and dust. Now, galaxies aren't all the same. The universe is full of different shapes and sizes, but most fall into three main types. The first is spiral galaxies. These are your classic pinwheels that have swirling arms of stars, gas, and dust spiraling out from a bulge in the center. The Milky Way and Andromeda Galaxy are perfect examples of spiral galaxies. In fact, they make up around 60% of the nearby galaxies we've observed. Likewise, there are elliptical galaxies. These are more of a smooth, football-like entity. These galaxies are home to older stars that have very little gas or dust, meaning there's not much new star formation happening. Their sizes could go from tiny dwarf ellipticals to massive giants. The most interesting of them all are the irregular galaxies. They have no symmetry, no clear structure, just chaos. Irregular galaxies often get their shape or lack of shape from gravitational interactions or collisions with other galaxies. Despite all that chaos, they've proven to be rich in gas and dust in order to fuel active star formation, which leads us into our very own cosmic neighborhood, the Milky Way. When you look into the night sky, you might see a faint milky band. That's our home galaxy. the Milky Way. It's a massive spiral-shaped collection of stars, planets, and cosmic dust that we have never been able to get to the bottom of. These arms of gas and dust, which are places where new stars are constantly forming, are called stellar nurseries. Estimates have shown that our galaxy contains about 100 billion to 400 billion stars, and the number of planets in it is just as astounding. Among all those stars is, of course, our Sun. Located in the Orion Arm about 27,000 light-years from the galactic center. The Milky Way itself is about 100,000 light-years in diameter. In thickness, it goes from 1,000 to 3,000 light-years. At the very heart of it lies Sagittarius A, a supermassive black hole which serves as the glue holding everything together. If we move 2.5 million light-years away from the Milky Way, the Andromeda Galaxy is its closest major neighbor. On a clear night, you can actually spot it with the naked eye. It appears as a soft and blurry patch in the sky. And just like the Milky Way, Andromeda is a spiral galaxy, but it's even bigger. Scientists have measured it to be 220,000 light-years across, which is more than twice the size of the Milky Way and contains about 1 trillion stars. Because of its complexity, it is one of the most studied galaxies in the universe, after the Milky Way. Now, this is where things get really interesting. Astronomers have discovered that the Milky Way and Andromeda are on a direct path towards each other. In about 4.5 billion years from now, the two galaxies will collide and merge to form an entirely new galaxy, nicknamed Milkdromeda, but it's not going to be as disastrous as you'd imagine. Despite their size, galaxies are mostly empty space, so individual stars are unlikely to collide. Instead, their gravitational forces will interact. Both galaxies will be reshaped, new stars will instantly form, and some stars will be thrown into completely new orbits. Our own solar system could end up in a totally different spot within the merged galaxy, or it might even be flung into intergalactic space. Luckily, we wouldn't even be around for all that. Oftentimes, in studies about our world, we forget that there are galaxies beyond ours. The Andromeda Galaxy is just one of the many that discoveries have led us to. The antennae galaxies are a pair of spiraling cosmic dancers locked in a collision, about 65 million light-years away in the constellation Corvus. Their name comes from their long tails of stars and gas shaped like antennas that stretch out into space by extremely powerful gravitational forces. These galaxies are a perfect example of what happens when two spiral galaxies collide. Their merger began about 500 million years ago, and the process has been nothing short of spectacular. When these two galaxies first began to interact, their gravity pulled and twisted huge clouds of gas and dust and compressed them into areas of intense star formation. The result is what we know as superstar clusters, where each is packed with tens of thousands of young active stars. What we see is a galactic evolution in action. Since the study of the antennae galaxies began, astronomers have been able to look into how collisions like this shape galaxies, grow them, and even cause the birth of new stars over billions of years. But there are even more. There are 3 other galaxies that hold beautiful secrets: the Large Magellanic Cloud, Messier 87, and the Triangulum Galaxy. This Large Magellanic Cloud is one of our Milky Way's closest neighbors, only that it is 163 light-years away. It is what is called an irregular galaxy, meaning it doesn't have the neat spiral shape of the Milky Way. Instead, it looks more like a cosmic cloud of stars and gas. The LMC is special because it's rich in gas and dust, so stars are having a field day, forming so very easily. It's also home to the Tarantula Nebula, one of the most active star-forming regions Earth has ever seen. And of course, there's a little twist. Scientists recently discovered that the LMC might have a massive black hole, which was quite surprising since these black holes are usually found in much bigger galaxies. Then there's Messier 87, or M87 for short. This galaxy is a giant located about 53 million light-years away in the Virgo cluster. Unlike the LMC, M87 is an elliptical galaxy shaped like a huge glowing football. It doesn't have the same spiral arms that the others have, but it is still quite stunning. The best feature of the M87 is probably the supermassive black hole at the center. How fascinating was it when in 2019, this black hole made history. It became the first one we ever captured an image of, thanks to the Event Horizon Telescope. And finally, there's the Triangulum Galaxy, also known as M33. This one's a bit closer to home, being just 3 million light-years away and part of our local group of galaxies, along with the Milky Way and Andromeda. M33 is a beautiful spiral galaxy, but it's smaller and less flashy than its big siblings. Still, it is full of star-forming regions, like the bright NGC 604, which is one of the largest stellar nurseries in the entire universe. But there are even much larger spaces where all the galaxies meet. These spaces are called supervoids. Think of the universe as a gigantic web where galaxies cluster together in really heavy knots and connect through filaments. In between those knots and strands are huge gaps called voids. When these voids get extremely big, as huge as over 300 million light-years across, they earn the title of supervoids. Now, supervoids aren't completely empty. They still have some galaxies and dark matter scattered around, but it still doesn't measure up to the cosmic average. The origin of supervoids goes all the way back to the Big Bang, in the chaos of the early universe. Little differences in matter density at the time meant that some areas had more matter, while others had less. So, over billions of years, the denser regions pulled in more matter to form galaxies and clusters, while the less dense areas stretched out and grew into voids. These voids merged over time to create the massive supervoids, which have also been classified into 3 types. The most prominent is the Boots void, also known as the Great Nothing. This supervoid measures 330 million light-years across. When it was discovered in 1981, it was found to contain only about 60 galaxies, when there should have been thousands. It's been about 40 years, and scientists have yet to figure out the reason for this anomaly. The Eridanus supervoid, on the other hand, is located in the constellation Eridanus. However, it is tied to something really absurd: the cold spot in the cosmic microwave background, which is the faint afterglow of the Big Bang. Finally is the 1.8 billion light-year supervoid. In 2015, astronomers found it to be the largest supervoid ever discovered. It measured 1.8 billion light-years across, but its size and emptiness have huge implications for cosmology, because it challenges the idea that the universe is evenly distributed on the largest scales. In fact, when we measure the expansion of the universe, supervoids, in general, play a huge role. When scientists study them, it refines their understanding of dark energy and how it makes the universe expand faster. Supervoids are so massive and influential that they push our current theories to the limit, and so understanding them could be tasking for scientists. But thanks to advanced telescopes and cosmic surveys, researchers are slowly putting all the pieces together. In the near future, supervoids may mean a lot more than they already do. Sometimes when we talk about galaxies, we imagine that they are just scattered randomly across the universe, but they're actually organized into a hierarchy. Individual galaxies group together to form galaxy groups. Those groups cluster into galaxy clusters, and multiple clusters come together to form superclusters. Now, these superclusters are connected by massive filaments of gas and dark matter to create the cosmic web that holds the universe together. Astronomers often use huge galaxy surveys to map out these superclusters, so they can pinpoint where they begin and end. Tools like the Subaru Hyper Supreme Cam have helped us discover even more distant superclusters. So how then do these superclusters form? Like many other things, it all started after the Big Bang. In the early universe, there were little fluctuations in the density of matter. Over time, gravity amplified those fluctuations and pulled the matter together into galaxies, clusters, and eventually superclusters. From what we have observed, these massive structures are still evolving. The galaxies and clusters within them still move slowly due to gravitational forces. The Laniakea supercluster is our home supercluster, and its name means immense heaven in Hawaiian, which is indeed a perfect description for its size. Laniakea spans about 500 million light-years and includes 100,000 galaxies, including the Milky Way. It was only just defined in 2014, so this is a relatively new way of understanding where we fit in the cosmic map. Before Laniakea was identified, we thought the Milky Way was part of another supercluster named the Virgo supercluster. This one spans about 110 million light-years. The Virgo supercluster includes the famous Virgo cluster, which is a dense collection of galaxies about 65 million light-years away. It also contains the Local Group, which houses the Milky Way and our neighbor, the Andromeda Galaxy. If you're looking for something further out, there's the Coma supercluster, located around 300 million light-years away. It's mostly known for the Coma cluster, which is a rich cluster of galaxies that has been key to understanding how galaxies are distributed and how they interact in larger structures. And finally, there's the Perseus-Pisces supercluster. This is one of the most massive superclusters ever discovered. It stretches over 250 million light-years. Its size and complexity make it a favorite for researchers who study the large-scale structures of the universe. Now, the way galaxies are distributed in any supercluster at all helps scientists find out dark matter, which makes up most of the universe's mass but can't be directly observed. They also leave us with clues and traces about dark energy, the mysterious force responsible for the accelerated expansion of the universe. And one of the most interesting recent finds is the Anasto supercluster, named after Estonian astronomer Jan Anasto. It's so massive that its mass is equivalent to 26 quadrillion suns and spans 360 million light-years. If the universe was a giant web, the threads would be galaxy filaments. These filaments form the boundaries between large, empty regions called voids. They're so large that some stretch up to 261 million light-years long. As always, the origins of galaxy filaments go all the way back to the Big Bang. After the universe exploded into existence, slight density differences caused some areas to attract more matter. Over billions of years, gravity amplified these fluctuations and pulled gas, dark matter, and galaxies into the web-like patterns that we have today. Astronomers first started to uncover these things in the late 1980s. In 1987, R. Brent Tully identified the Pisces-Cetus supercluster complex as one of the first hints of the cosmic web. 2 years later, the CFA-2 Great Wall was discovered as the first super-large structure found in the universe. Fast forward to 2003, and the Sloan Great Wall took over as the largest structure known at that time. Today, things are a bit different. The Hercules Corona Borealis Great Wall is the heavyweight champion of the universe. When it was discovered in 2013, it could stretch as far as 10 billion light-years. Eventually, it became the largest known structure in the cosmos. The Sloan Great Wall is another galaxy filament. It spans about 1.4 billion light-years and was discovered in 2003. Around this time, it held the title of the largest known structure after the CFA-2 Great Wall, also known as the Coma Wall. This was the first of these gigantic structures to be identified, way back in 1989. It stands at 819 million light-years long and is still identified as the one who set the stage for everything we've learned about the large-scale structures of the universe since. As the largest structure in our universe, they are the answer to some of our curiosities. You see, the movement and alignment of galaxies along filaments give clues about how the galaxies form and evolve over time. These structures are all part of the puzzle when it comes to understanding how gravity shapes the universe on a massive scale. As a matter of fact, recent discoveries show that galaxy filaments do rotate. As giant strands of matter, they spin and pull galaxies into their orbit. As enormous as our entire universe is, most of it is just empty. When you break it down, the actual stuff in the universe, the stars, planets, galaxies, and gas, are just a tiny fraction compared to the measure of nothingness. Even in galaxies, where stars and planets are relatively close, the gaps between them are enormous. The Sun is about 93 million miles from Earth, but the nearest star, Proxima Centauri, as we have discussed, is over 4 light-years away. Outside a galaxy, the emptiness gets even more extreme. Galaxies, supervoids, and superclusters are separated by millions of light-years of mostly empty space. In fact, ordinary matter, which is the matter we can see and touch, makes up only about 5% of the universe. The rest is just dark matter and dark energy that we can neither see nor fully understand. But even with those, most of the universe is just nothing. Thank you for watching. If you enjoyed this, like, share, and subscribe for more videos about the wonders of the universe. See you soon.